In sections 1 through 3 of chapter 17, we'll discuss the entropy change for the system, the surroundings, and the universe. Spontaneous processes, or thermodynamically favored processes, occur without outside intervention, so without added energy. Thermodynamics will predict if a process is spontaneous or not, but it doesn't tell us anything about the speed, the kinetics of the process. So therefore, spontaneous processes can actually be fast or slow. This graph has a thermodynamic part and a kinetic part. If you remember, we, in an earlier chapter, talked about activation energy as a means of determining rate of reaction. That's our kinetics part of our graph. That's our pathway from reactant to product. And in an earlier chapter, we also talked about the enthalpy change between reactants and products to determine if we had an endothermic or exothermic reaction. That's the thermodynamic part of the graph. We'll be able to use thermodynamics to talk about if a process is spontaneous or not, but we don't need to have any knowledge of this pathway in between. We don't really need to have any knowledge of the kinetics part of the graph. However, to describe a reaction fully, we really do need both thermodynamics and kinetics. To determine if we have a spontaneous process, we're going to look at something called entropy. We use a capital letter S to represent entropy, and it is a measure of randomness or disorder. So when we have a spontaneous process, we should always see an increase in entropy for the universe. When we think about the entropy of a system, we can think about how many arrangements there are available to the system, and that nature will spontaneously proceed toward the states that have the highest probabilities of existing. More on that here in just a moment. First, let's talk about positional entropy. Gases have the highest positional entropy. Those particles, if you recall, are the farthest apart. They would have the most positions available compared to liquids and solids. In general, for gases, if you increase the volume, you see an increase in entropy, an increase in disorder, because you have more space for the particles to be disordered in. And if you increase the temperature, you see an increase in entropy. For a gas, the gases can move around more at higher temperatures. So now let's talk more about possible arrangements for particles within a system. If we have a gas and it's just on one side of the chamber, if we open up the valve, basically what we are going to see is that we have a uniform distribution of particles between the two chambers. That corresponds to the state that has the highest probability of existing. And nature will spontaneously proceed toward the state or states that have the highest probabilities of existing. There are actually more ways to have the particles distributed. For example, take a look at the possible distributions of 4 different particles. So they can all be on one side or the other. We can have a 3 on the left, 1 on the right distribution, or a 1 on the left, 3 on the right distribution. There are 4 different possibilities of arranging those particles, A through D. But if you have 2 and 2, if you have uniform distribution of the particles, we see the most possibilities for that. This is the greatest number of possibilities, so it is the most likely arrangement that we will see. Let's end this section with predicting the sign of the entropy change for each of the following processes. For the evaporation of alcohol, we're going from a liquid to a gas. Gases have the highest positional entropy, and so that is an increase in entropy. That will be a positive sign. For freezing of water, this is a liquid to solid phase change. We should see less disorder as we go from a liquid to a solid and the particles get locked into place and just vibrate. So that's a decrease in entropy. We should see a negative sign. Compressing a gas at a constant temperature. The gas has less space, so there's less disorder. That's a decrease in entropy with our decrease in volume. That should be a negative sign. Heating a gas at constant pressure, particles move faster, we should see more disorder, and increasing the volume when we heat a gas at constant pressure means more possibilities for disorder as well. So that one should be positive. And dissolving sodium chloride in water, sodium chloride will dissociate or break apart into ions when it dissolves in water. That creates more disorder, and that should be a positive entropy change. In section 2, we're going to discuss entropy and the second law of thermodynamics. The second law of thermodynamics says that the entropy in the universe is always increasing. Remember, the first law of thermodynamics states that energy is conserved, or the energy of the universe is constant. So the second law talks about entropy, and it should be increasing, so not conserved, not constant. We could talk about the entropy change for the universe in terms of the entropy change for the system plus the entropy change for the surroundings. In the previous section, we just looked at entropy changes for systems for different processes, and we'll talk about the universe entropy change and the surroundings entropy change coming up in future sections here. When we see an increase in entropy for the universe, that is a positive sign. When we see a decrease in entropy for the universe, that is a negative sign, and that means that that process is not spontaneous or not thermodynamically favored. When the entropy change for the universe is 0, that means the process has no tendency to occur, or that the system is at equilibrium. In section 3, we're looking at the temperature dependence of spontaneity. In particular, we'll look at the entropy change for the surroundings and be able to bring that in with the entropy change for the system to talk about the entropy change for the universe. When heat is transferred into or out of the surroundings, we see a change in the motion of the particles, the randomness, the disorder of the particles. And so the sign for the entropy change for the surroundings will depend upon if heat is transferred into or out of the surroundings. The magnitude of the entropy change for the surroundings does depend on temperature. The lower the temperature, the slower the motion of the particles. So even a small transfer of energy will increase the motion of those particles. So that means that the impact of the transfer will be greater at lower temperatures. So for an exothermic process, an exothermic system, that means that heat leaves the system and goes out into the surroundings. And so the random motion of the particles starts to increase with that increase in temperature. And so the entropy change for the surroundings should be positive. For an endothermic reaction, an endothermic process, heat goes from the surroundings into the system. And so those particles start to move more slowly, less random motion. And so we see a decrease in the entropy for the surroundings. You can put these ideas together in this equation right here. If you think about the enthalpy change being the heat transfer, like we have in a previous chapter, we get delta H over T. Temperature should be in Kelvin if you're actually going to calculate this out. And notice this negative sign right here so that we can focus on the surroundings. The enthalpy change is for the system. So negative for an exothermic reaction. A negative will give you a positive entropy change for your surroundings. If you look at the change in entropy for the system and for the surroundings, add those quantities together, you can talk about the entropy change for the universe and talk about if it's increasing or decreasing. So in this little chart, we kind of have summarized all of our different possibilities. If the entropy for the system and the surroundings are increasing, positive, then we will get a positive answer. And when we get an increase in the entropy for the universe, that is a spontaneous or thermodynamically favored process. If both are negative, when we add them together, we get a negative entropy change for the universe. And that is not a spontaneous process. However, the opposite direction, the opposite process would be spontaneous. When you have one of each, one positive, one negative, it's really kind of open in terms of if you have a spontaneous process or not. And basically the positive value, whichever one it is, has to outweigh the negative value in order to give a positive answer. So for this one, if your system magnitude, the number, the one that's positive is larger than the negative one, then you get a positive answer. So yes, spontaneous. And then for this one right here, the positive value is the entropy change for the surroundings. If the magnitude, if the number of that is larger than the number for the entropy change for the system that's negative, then you get a positive answer. And then yes, the process is spontaneous. Finally, let's think about if the following describe a spontaneous or non-spontaneous process. When we look at if something is endothermic or exothermic, remember we can use that to determine the entropy change for the surroundings. And then positional randomness we can look at in terms of the entropy change for the system. And then if we add the two together again, that gives us the entropy change for the universe. For spontaneous processes, we're looking at a positive value there. So exothermic processes, for the surroundings, that gives us an entropy change that is positive. Again, heat is coming into the surroundings. The particles start to move faster. There's more randomness there. So that's an increase in entropy for the surroundings. And then for the system, more positionally random means an increase in entropy. So that one is positive as well. So two positives added together gives you a positive answer. Letter A would be spontaneous. For B, less positionally random means negative. And so a positive and a negative added together, it's hard to tell. Okay. For C and D are both endothermic, and those would both be negative entropy changes for the surroundings. Heat is leaving the surroundings, going into the system, and so those particles have less randomness in terms of their motion, and that is a negative entropy change for the surroundings. More positionally random, again, is positive, and less positionally random is negative. So for letter C, a positive and a negative added together, hard to tell. For letter D, though, we're adding together two negative values, and therefore that would not be spontaneous. You get a negative entropy change for the universe.